In this video, we'll go through a full example of how to make a trig model of data that seem to have a periodic character that would be best modeled by a sine or a cosine. And we have here some data on average daily temperatures for the Twin Cities. The average daily temperature is simply the average of the high and the low for a given day. And for a month, of course, it would be across all those days. And so we have in the right-hand column of this table the average daily temperature for each month, January through December. And of course, the first thing we have to do if we want to make a numerical model is to render the months into some sort of numerical scheme, and so we'll just number them 1 through 12 as is customary. And then we can start working out the various values that we're going to need in order to make our model. And so the first thing we might check out is the amplitude. The amplitude is half the difference between the largest and smallest values. And if we just scan this right-hand column, we find that the greatest of these average monthly daily temperatures is 73 in July, and the least is 13 in January, not surprisingly. And so we will have 73 minus 13 all over 2, which is, of course, 60 halves, or 30. The period, since we're working in months and this is an annual cycle, will just be 12. The vertical shift will be the average of the maximum and minimum, and so it will be 73 plus 13 all over 2. That's 86 halves, or 43. And then the phase shift will depend on the choice of parent function. But if we were to choose the cosine, then it would just take us out to this maximum in July, and that would be 7. So our model is going to be an image of the cosine function under a transformation. And once we can say what that transformation is, then we can just reverse everything and we'll have the equation. So the scale change to x is the only thing that really requires a little thought. It's going to be whatever scale factor a turns 2 pi into our period of 12. And that's going to have to be 12 over 2 pi, which is 6 over pi. So we have 6 over pi times x. The horizontal translation, of course, is the phase shift, which is 7. And then to y, we have a scale change of 30. That's given by the amplitude. And then we have to go with our vertical shift of 43. So our function should be the cosine under this linear transformation. And now what we have to do is to reverse everything. So in the case of y, to undo multiplication followed by addition, we will subtract and then divide. And similarly for the cosine, or for the x rather, which is the object of the cosine, so we'll have x minus 7 all over 6 over pi. And probably for daily use we would want to clean that up, so we could multiply by the 30 and we could add the 43. We would have y equals 30 cosine. We can clean this up a little bit also, since dividing by 6 over pi is the same as multiplying by pi over 6. We can make that little change and resolve the complex fraction, and then we'll have to continue with adding 43. Once you have your model, you can test it, of course, by graphing it with the data. And so I have these values entered in my calculator, and I have a scatter plot that, as you can see, matches the printed graph. And I'll just go up and enter 30 cosine of pi over 6 times x minus 7, making sure I take care of the order of operations, plus 43, make sure I'm in radian mode, and my graph should hit my points. And it's not a perfect fit, but it's pretty good. And that concludes our example.